Hey biologist. In lab 7.1, we explored the question, can water and oil ever form a stable mixture? And in quiz 8.1, you're going to answer some questions related to this homework from lab 7.1. In previous activities, you explored how water and oil don't mix. Remember, we found that oil sits on top and water is on the bottom. Water is dyed blue here. Even if we shake it up, they very quickly start to separate and the oil starts forming its own separate layer on top within, seconds of being mixed. You've seen demonstrations showing that shortly after you mix oil and water together, they separate into two layers containing water and oil molecules. As you concluded during the activity, this is the result of attractive forces between polar water molecules being stronger than the attractive forces between polar water and non-polar oil molecules. Remember, water molecules can stick together because they're polar. This oxygen here, represented by the red ball in the space-filling model, the electron, the negative electron, spends more time with oxygen because it's bigger and can attract the electron more strongly. And so oxygen becomes negative because it has extra electrons, which are charged negatively, and hydrogen becomes positive, and they stick together. Nonpolar molecules aren't the same. They don't really stick the same way. And polar and nonpolar really don't stick together either, in the same way that polar molecules stick to polar molecules. This is in fact due to the attractive forces between permanent partial charges in the polar molecules, which are stronger than the attractive forces between temporary partial charges that form with nonpolar molecules. We just talked about that with our molecular models here. Therefore, soon after you stop swirling or shaking the mixture, which forces the water molecules to mix with the oil molecules, the stronger attractive forces between the water molecules cause them to aggregate back together, forcing the oil molecules out. And indeed, the test tube that we just shook up has separated again into oil and water. Oil molecules, in turn, form intermolecular forces with each other via temporary partial charges, like you see here. These are the polar water molecules sticking together with very definite plus and minus charges, plus sticking to minus, and oil really is pretty neutral, so it forms temporary bonds, but they aren't very strong. This general mechanism can be used to describe why any polar substance doesn't mix well with a nonpolar substance. There are just much stronger attractions between the polar molecules, and they squeeze out the more weakly attracted nonpolar molecules, just like we were talking about with proteins. However, in fact, despite that polar and nonpolar molecules don't form stable mixtures on their own, there are plenty of examples of substances containing polar and nonpolar molecules permanently mixed together. Some examples include mayonnaise, chocolate, ice cream, various salad dressings, and a lot of baked goods. So what happens when you form a stable mixture of polar and nonpolar molecules? It is possible to get oil molecules to stay mixed with water by introducing another type of molecule that can interact both with polar water and nonpolar oil molecules. This is a special type of molecule that helps stabilize water-oil mixtures, works like a glue, forming interactions both with polar water molecules and non-polar oil molecules. Take a moment to think about what structural characteristics that molecule should have in order to form an interaction both with polar and non-polar molecules. We talked about in class that these molecules have sort of dual personalities, or we can call them peacemaker molecules, because they can interact both with the non-polar molecules and the polar molecules, because they are molecules that have both a polar end and a non-polar end, and they line up in a very special way when they encounter polar and non-polar molecules. The molecules that help stabilize water-oil mixtures have both polar and nonpolar regions. One of the molecules we talked about in class is soap or detergents, and this is what we use to mix water and oil in our lab. Soap has a polar head that can interact with polar molecules like water, and a long nonpolar tail that can interact with nonpolar molecules like oil, as shown in the picture below. So here's soap, particularly stearic acid. The nonpolar tails are sticking into the oil glob, and the polar end of the soap is sticking out towards the water. This is how you get oil and water to mix. So here's oil and water. Here's oil and water and soap mixed together. You can see that yellow and blue are very separate here, but together yellow and blue make green when they mix up with the soap. Soap is mixing up the oil and the water. It's exactly the same test tube, a little bit different volume because I added some soap, and the suds make it look different. But this is oil and water mixed with some soap, and this is just oil and water. Because soap has special properties, it's got a polar head and a nonpolar tail, it can get oil and water to mix. When adding a water-oil mixture, the nonpolar tails of these molecules interact with oil molecules, and polar heads interact with water molecules, forming structures such as the picture below. This is called the micelle if you want to get fancy. The nonpolar is with the oil, and the polar end of the soap is with the water. Now the oil has polar parts sticking out of it, allowing the entire oil droplet to stay suspended in the water, just like we see here. Oil is being suspended in the water using soap. This special kind of molecule that stables polar-nonpolar mixture is called an emulsifier. An emulsifier helps prevent the polar and nonpolar liquids from separating into two layers. We use a common emulsifier a lot when we bake. If you've ever made a recipe that called for oil and water, you probably put an egg in it. Or if you're vegan, maybe you put in a banana, and that gets the oil and water to mix when we are cooking. An emulsifier helps prevent the polar and nonpolar liquids from separating into two layers. If you don't put an egg in, you might get really oily, weird muffins or pumpkin bread or whatever you're making. If you've ever read the ingredient list of any products mentioned above, you'll see lecithin listed. Lecithin, which is most commonly comes from soy, is a blend of naturally occurring molecules which act as emulsifiers. They have a general structure as shown in the picture above, with a long nonpolar tail. This nonpolar tail can mix with oil, and the polar head can mix with water. They help ice cream, chocolate, and other foods maintain a familiar texture instead of separating into oily glop and watery glop. That'd be gross. You can see here's a box of baking chocolate, and they have lecithin in the chocolate as an emulsifier. The food industry is not the only one benefiting from emulsions. For example, in medicine, emulsions are used for intravenous injections of various drugs. If you have a nonpolar drug, most of our body is water, so somehow you have to get that nonpolar drug into a polar environment and get it to mix properly with your polar water inside your body. Many personal care products are also emulsions, including most creams, lotions, and ointments. If you look like maybe at your lotion, it might have lecithin as an emulsifier in it, or maybe they used something else. So we don't have to do this question, but there is a quiz, and I've gone over much of what you need to know for the quiz. So now you're all ready for quiz 8.1. Thanks so much for watching. This is Dr. B signing off.